So today we're going to talk about optimization, which is the beginning of our section 4.2 and really some big ideas in chapter 4. But just so we're all on the same page, in math class, optimization means we're looking for a value that's either the biggest value or we're looking for something that's like the smallest value. So just a quick example, when I optimize something, like for example, if I was trying to optimize profit, the goal there of optimizing profit would find the biggest number that would represent my money. So I want to find the biggest amount of money I could make. But maybe I'm trying to optimize something like my race time. If I was trying to optimize something like my race time, it'd be the smallest value. So we can see the idea of biggest or the smallest is fine. So for today, we're just going to kind of focus essentially on that biggest and smallest value. And we know that maximums and minimums, biggest and smallest, are just called extrema. So our first part is just like vocabulary. So we're going to look at local minimums versus global minimums. Same thing with maximums. So we've already kind of went over the idea of local minimums as with some of our work with the first derivative. But the idea with a local minimum is that something is a local minimum if it's the smallest value around it. So for example, let's look at this point here. This point here, although it's not labeled for us, this point here I would consider a local minimum because it's the smallest value around it. So if I look a little bit this way, like over here, if I look in the general vicinity around this area, it's the smallest value. Now if I go too far, I can find some other smaller values, but that's the idea that we're looking for in the definition, is just around P, or around that point. And the distance that we travel around that point is just obviously up to us, but just around, this is the smallest value in this general vicinity. There's nothing smaller around it. Same thing with the maximum. So if I look at something like this point over here, this is a local maximum, because if I look generally around it, so if I go a little bit to the left of that point, these y values are smaller. If I go to the right of that point, these y values are all smaller. So in other words, around or near that point P, this value here is either greater or the same than everything around it. And we compare that to the idea of a global minimum. So a local maximum minimum is just looking around P. So the idea is like we're just looking at a small interval around there. The idea with a global maximum or minimum is we're looking at all values of the function. So you can think of it like over the entire domain. Whereas when we're looking at the local maximums or minimums, this would just be a section of the domain. So if I look at this entire graph, there's a local minimum in this little, local maximum in this little area, so between like -8 and -6. That's the biggest value around that neighborhood. But if I'm looking for the global maximum, I'd have to look over the entire domain, and the entire domain goes from -10 all the way over to 8. So if I followed every single input, what's the biggest value? That'd be our global maximum. So this point right here would be our global max, because the value there, the output of 9, is bigger than or equal to all the values of f. This over here would be our global minimum, because if I consider every single input that existed into my function, the smallest output value is -8. So just a difference between local minimums and global minimums. Same thing with local maximum and global maximum. And we talked about local extrema using the first and the second derivative test. So today we're going to talk essentially about global extrema. But the idea here is we're going to consider two different types of intervals, either opened or closed. So the first one we're going to start with is a closed interval. So just as an example, like if you give yourself, or I have it in the definition, what I mean by a closed interval is the endpoints are included. So what we are saying here is if f is continuous, if we have a continuous function on a closed interval, then this rule will guarantee that f has to have a global maximum. And here that word has is we're guaranteeing the existence. And that's kind of important to make sure, is that we have a rule to show that it'll always exist. So in other words, what we're saying is if we pick a starting point, so I'm going to have an interval that starts at A and it goes to B. Now the first part is it's close, so we have some sort of definition here at A, so we know that the point at A exists. Now if f is continuous, we have a smooth connected graph from where we started all the way over to where we finished. So no matter how I determine to draw this, my graph is smooth. Because it's connected between every single point, there has to be a biggest and a smallest. So like for instance here, that's one example. I can see that the maximum is right there, and it looks like that's the minimum. So this has a global maximum and a global minimum. There also are more local maximums and local minimums, but if I look at the entire function, I can see the global max and minimum. So again, it doesn't matter how we draw it. So what we're saying is if you pick a starting point, and you can't pick up your pencil until the ending point, no matter how I determine to draw that, there has to be a biggest point and a lowest point. So again, here I can see that my maximum is up here, and my minimum is actually right here. Now, there could be a weird function, right? Like from A to B. What if I just drew this? This is a continuous function on that interval. Does it have a smallest value? Yeah, right there. Does it have a biggest value? Well, it's the same. So here the max and the min would be the same value, and it would occur everywhere, but there still is the existence of a global minimum and a global maximum. So with that idea, if we're going to think about where would those global extrema be, so again, I'm going to draw one, well, let's just listen. Where could we possibly think of for global extrema? Well, the first thing we want to calculate is we want to find critical points. Because we know from the first derivative that the critical points are where we're going to find any sort of local extrema. And at this point, we only know if they're local. So in other words, where could extrema be? Well, it could be where we were looking for before. It could be where the derivative is 0 or undefined, where we see that sign change. So we'd want to look for the critical points. But then we'd also want to consider the endpoints too, because those endpoints are defined, so maybe those are bigger than the extrema in the middle. So again, if we're going for an example like this one here, I'll draw a new one. Let's say, let me get rid of this here. Let's say we have some graph that's defined on a closed interval from A to B. So again, it doesn't matter what graph you draw. So here's my graph from A to B. So A starts down here and it goes up for a little bit here, and then maybe it stops right there. So if there is going to be extrema, the place I'd want to look first is the critical points. So using my first derivative test, that extrema, that extrema, that extrema, and that extrema will all be flagged by the first derivative test. I guess we should say those will be critical points. So we'd use the first derivative to find the critical points. Now, those are the only places that we'd really need to look if we're thinking about just the extrema in between those intervals. But since the interval is defined on A to B, these are the candidates for the extrema inside the interval. Well, then we just want to compare those values. So we can see that right now, if we look at just the local extrema, well, we can see that this one right here is obviously the biggest. And that's what would come up from our first derivative. We'd be able to see those critical points. However, we do want to compare it to the endpoint. So it's higher than that, and it's higher than that. So in this case, our critical point was one of the local extrema. It was right there. There are some other cases, like we saw, that I could draw. So maybe I'll just draw another graph over here. So if I drew something like this, I'll just move the graph down actually. If I drew a graph that looked like this, and let's say it starts here at A, and it's continuous all the way down there to B. if I use the first derivative and I ask where could the extrema be, the first derivative would point out that point and that point right there. So it wouldn't actually show me any maximums, but if I considered the endpoints, I could see that this is clearly the biggest value right there. So I do want to consider not only the critical points that would come from the first derivative, so those would be candidates for maximums and minimums, but then also just to compare them to where the function started and ended, in other words, the endpoints of that function. Now we have to consider what would happen on an open interval. So the idea with an open interval is that we are not defining the function at its endpoints. And that's what I'm saying here. We're not including the endpoints of that function. Now when that happens, it's not quite as straightforward. There could, or maybe there isn't, a global maximum or minimum. So like just as an example, so we're looking at a closed interval, or sorry, excuse me, an open interval. So let's say the interval starts here and ends there. There's a few different cases that we could consider. So let's kind of look at a case that would have. So let's say we look at a graph like this. So something like this, if I try to define the interval on which it is, which the original function is defined, the interval that's defined is from negative infinity all the way to infinity. So I'm not including the endpoints, so by definition this is an open interval. But as I'm trying to draw here is that the endpoints, they have that horizontal asymptote, so they're getting closer and closer to 0 there. Same thing over here. So I can clearly tell that this one has a global max. I could draw another example, like let's say this is the point A and this is the point B, and rather than approaching infinity, what if there were asymptotes there? So if I drew a graph that looked like that, let's say something like this. So these are approaching the asymptotes there. So with something like this, the interval that it's defined on is from A to B, but there's vertical asymptotes at A and at B, so that's why we're not including the endpoint. So something like this, I can clearly see that there is a global minimum. However, if I asked what's the biggest value that exists here, I couldn't tell you because these graphs keep going forever and ever. So the idea here is that there could be or there could not be a global maximum or minimum. So we have to do a little bit more work. But the idea here that we'd want to check, and we'll see some more examples of this, the places that we want to check for this, we obviously want to check the critical points of the function. Those are the candidates inside that interval where we're going to see bumps or kind of valleys per se. So we obviously want to check the critical points. However, then what we want to do, we can't evaluate the endpoints. Just like we did before in the closed interval, we tried to evaluate the endpoints. However, in this case, the function's not defined on those endpoints. So what we do is we're going to look at the values of the function as x approaches those endpoints. Now in some cases that endpoint might be a defined number like -3 or -2, kind of like over here that endpoint was just a and b, or maybe that open interval goes from negative infinity to positive infinity. But we want to just look at the values to see what is the function doing. So like for example here, I could clearly see that this would be labeled as a critical point using that first derivative. So I know that this could be the the global minimum. But what I need to do though is say, what is my function doing around that though? So if I continue to go this way forever, I can see that the values are only getting bigger. If I went and considered the end behavior near A, those values are only getting bigger. So I started with that critical point right here and said, okay, that's probably the minimum, but just to make sure, let's look at what's happening around that. So I do want to draw another picture of those. So let's consider something like this. So if we have a graph, and let's say, I'm just going to kind of draw something that looks like this. And let's say here, just for the sake of this, let's say that this is going to go up forever, and this will go up forever. So in other words, this function was just defined on an open interval from negative infinity to positive infinity. So if I was going to find where would the maximums or minimums be globally for this function, I'd look at the first derivative and find the critical points and say, okay, well, these are the candidates. This is where I would think I would find my extrema. So for something like this, I can clearly see that this is a local minimum. But before I can say it's a global minimum, I'd have to say what is the end of my function doing. So as I progress towards positive infinity, my function is only going to get bigger and bigger and bigger. If I progress towards negative infinity, my function is only going to get bigger and bigger and bigger. So I can see, I've just kind of proved, because I considered the endpoints, right? F of x will just approach infinity from both endpoints. So there's never going to be any smaller value than this. So this is our global minimum. However, this candidate up here, while it was flagged as a local maximum, what we would see is because the function continues to rise, this is only a local maximum. And same thing here, this would only be a local minimum. So another example that I think is important to go through, which is really conceptual as to why sometimes it might not exist. Let's just look at the line. I'm going to say I'm going to define this line from negative 10 to positive 10. I'm going to say this function, f of x, is just equal to x, but it's only on the interval from negative 10 to 10. So I'm just going to set up a nice coordinate plane here. So in other words, right here, the function's not defined there, and it's not defined at the other point of negative 10, positive 10. So in other words, what we can see is that this function isn't defined at those endpoints, but it's just a straight line going through the origin in between them. The idea here is, what's the smallest value on this entire graph? Well, the problem is that we can't actually define that. It was one of those endless limits. So we can get really, really close to negative 10. So like if I plug in something like negative 9.9, it looks like the smallest value then is negative 9.9. But the question becomes, how close can you get? So if I do this, well then you would say, well, that's the smallest value then. And then somebody else would come along and say, no, I actually found another value that's actually smaller than that. They'd add another 9. So the idea here is we would never be able to end this argument. What is the smallest number that's not 10 but closer to 10? Well, that's a never-ending argument. We can never say what the smallest number is. Whatever number you give me, I just add a decimal place and make it a little bit smaller. We can't use an inequality. Like we can't say something like the smallest value is something that's bigger than negative 10, because this isn't one value. This is an infinite number of values. So again, the idea of the end behavior is we can't always consider that a value because we don't know what it's defined. And the same thing happens up there with the biggest value. If I asked you what's the biggest output, well, someone could say, well, 9 is pretty big. I could plug in 9 and get the output of 9. But then somebody would say, well, I could do 9.01, and that's actually a little bit bigger. And then somebody comes along and says, well, I can find an output that's bigger than that if I plug in 9.1. That output's bigger. But again, this is a never-ending argument. If you choose this number, and you see that, okay, my output's the biggest now, I just choose a number that's a little bit bigger. Maybe I add a decimal point, or make it just slightly bigger. So this argument would never end. So something like this, there's technically no global extrema because of that argument.